In this video, I'm going to go over how to draw resonance structures of compounds. So oftentimes when we draw bond line structures in organic chemistry, the structures can't tell the whole story. They're not really adequate because some compounds can have multiple resonance structures. And the overall structure of the compound is like a blend of these resonance structures. And you'll see more what I mean when I go into them. So for example, if we've got this compound here, so the positive formal charge is telling us there's only one hydrogen on that carbon. So it has a formal charge of 4 valence electrons minus 3 assigned electrons, so we have a positive. This is in resonance with this structure. I can draw the 2 electrons from that pi bond moving over. And instead now, I get that as my resonance structure. This is the same compound, just 2 different resonance structures of it. And I draw these double arrows because the compound is going to show characteristics of both of these resonance structures. It's not one or the other. It switches between these. Now, it's going to be favoring this resonance structure, or we'd say the one on the left is the better or best resonance structure, because as you've learned, a secondary carbocation is more stable than a primary one. So we would expect that the structure on the left is going to be more indicative of what the overall nature of the compound is than the one on the right, but it will switch between both of them. Okay, so this arrow that I draw, right? The arrow that I draw for the resonance structures. The tail end here is always at the electrons. So this could be, a lone pair or, pi electrons from a pi bond, as in the above example. So the tail is always from the electrons. The head right here is where the electrons are going. So the head's where the electrons are going. And notice the arrow, right? It's a full arrow, meaning it's a 2 electron transfer. This isn't a radical transfer with the fishhook arrows. It's a 2 electron transfer indicated by the full arrow. So another example will kind of show what's going on with the arrows here. Right, this would be in resonance. I'm going to move that over. In resonance with that compound. And again, we'd predict that this is the best structure because it's a tertiary carbocation versus a primary one on the right. Now, as I've shown in the past 2 examples, you need to indicate the formal charge when there is a formal charge. So I'm indicating the positive formal charge on the tertiary carbocation and then the positive formal charge on the now primary carbocation. Also notice that formal charge is always conserved. So whatever my formal charge is for the overall molecule in the first structure, all the resonance structures must also have that same formal charge. So another example, I'm going to start with a compound that initially has 0 overall formal charge. There is a resonance structure I can draw here. This would be in resonance with this compound. The overall formal charge is still 0. I just have +1 minus 1 to give me 0 on the right. Now we would say this one here is the best resonance structure because we don't have any formal charge on an individual atom. And towards the end of the video, I'll go over the different rules for determining what the best resonance structure is. But because this has no formal charge on any of the atoms, we consider that the best resonance structure. But again, the compound is going to show characteristics of both of these resonance structures. Now, something important to note with drawing resonance structures is that you can never break a single bond. So single bonds can never be broken. There's two reasons for this. One is the energy required to break a single bond is very large. So that's the first thing. And secondly, as I mentioned right in the beginning of the video, resonance structures are the same compound. If you break a single bond, you no longer have the same compound. You've made two new compounds. So that's another reason you cannot break a single bond in a resonance structure. So you'll never see, this. Right, that will not happen. Likewise, you wouldn't get, isopropanol here. There's no resonance structure. Well, I didn't draw the arrows on this first one. Right, so I was doing that for the first one. The second one, you're not going to get a resonance structure where you end up getting a carbocation and hydroxide. That will never happen either. Right? You cannot break a single bond in a resonance structure. Another rule: you cannot exceed an octet for second row atoms. And by the second row atoms, primarily we're talking about carbon, nitrogen, and oxygen. They cannot have an octet, or you cannot exceed the octet. You want to have the octet, and you can have a valid resonance structure where you have fewer than an octet, right? That's a carbocation, but you cannot exceed the octet. So I'll show that with this example here. I cannot draw a resonance structure where I move that pi bond over. So now I have a carbocation there, and then a negative charge, formal charge there. And I'm going to switch it from bond line structure to the full structure with the atoms to show why. So this first compound, we got the alkene, and then two methyl groups right on each end. We're saying that this is in resonance with, I'm going to move this pi bond over to here. So now, I haven't changed the methyl group on the left at all. This is now a carbocation because it only has 3 bonds to it. The problem is right there. I have 5 bonds drawn to that carbon. So I've exceeded the octet. And I cannot do that for a second row atom. The reason being, right, carbon has electron configuration of 1s2, 2s2, 2p, 2. Yes, 1s2, 2s2, 2p2. It doesn't have the ability, like when you hybridize this, right, I have the 1s2, and then I have the sp3 hybridized orbital. I cannot accept more electrons than this orbital can handle, right? And I'm going to have too many electrons if I exceed the 4 bonds to it or the 8 assigned electrons. So you cannot violate the octet for carbon, nitrogen, oxygen, any of the second row ones. Once you get past the second row, then you have extra empty orbitals available where you can now exceed the octet. But you cannot do that for carbon, nitrogen, or oxygen. And if you want to go more into the details of why that is, with a video on the different, electron configurations and the orbitals, you can go ahead and do that. But yeah, you cannot exceed the octet for carbon, nitrogen, or oxygen when you're drawing these resonance structures. Okay, another rule with resonance structures is that there cannot be 2 double bonds next to each other in a ring. So this is tricky because the resonance structure may be valid. So say I have that, and I draw a resonance structure where I end up getting this. This seems like it's not violating any of the rules we've said, right? So it seems like it can be a valid resonance structure. The issue is that 2 double bonds next to each other has to be linear. But when you're in a ring, you can't be linear, right? You're required to have a certain bond angle given that you're in a ring. So you cannot have 2 double bonds next to each other in a ring. So this would not be a valid resonance structure. You would have to stick with that. Another thing with resonance structures is you can have multiple arrows. But you can draw more than one arrow at a time, and I think I've already shown that in one of the examples. So say we have a compound we have that compound. I can draw a resonance structure here where I move 1, 2, 3, 4 pairs of electrons to now give that as my other resonance structure. All right, those are 2 resonance structures of each other. This would be what's called a conjugated system. You have multiple pi bonds in conjugation with each other, and you know it's conjugated because you can draw multiple arrows. So don't be afraid to have to move multiple arrows when you're drawing a resonance structure, because it's certainly valid to do that. All right, last thing I want to go over is some of the rules for determining what the best resonance structure is, because you may often be given questions asking which resonance structure is best. Like you're asked to draw all of the resonance structures and then you indicate which one is best. Okay, so rule number 1 is going to be that usually resonance structure with no formal charge is best. And this means no formal charge on the individual atoms. So for example, I've got a resonance structure that I can draw here so this would be benzaldehyde. I could draw a resonance structure here where I move those electrons there, those up there, and those there. And this would give me a bond, pi bond there and there, double bond there, negative charge on the oxygen, and then a positive formal charge there. Now I could also draw another resonance structure where I bring these electrons back down and I move one of the electron pairs over to the ring again. So now I have basically the same structure I did in the first one, but the double bonds are in a different location on the ring. Both 1 and 3 here would be considered the best ones. There's really no difference between 1 and 3. The electrons in the ring are delocalized, so they can constantly just have a resonance structure where they move around the ring. So both of those, 1 and 3, would be the same resonance structure, and it would be the best because they don't have formal charges on the individual atoms. Now, second rule is going to be if there is an overall charge, right, this means that you'll have to have a non-zero formal charge on an atom. The negative formal charge, assuming there is a negative formal charge, should be on the more electronegative atom. So in this example, say I have this would be in resonance with this guy. So notice I'm not moving the electrons from this pi bond over to this location, right? Because I can't do that or else I'd exceed the octet, but I can make it a lone pair on this carbon. So now I'll get the negative formal charge on that carbon. This would be the resonance structure because the negative formal charge is on the oxygen, which is the more electronegative atom. So last thing to mention about resonance is that resonance stabilizes compounds. Stabilizes compounds by delocalizing electrons. So all delocalization means is that the electrons can move around. It spreads out the electron density, the electron charge, and that stabilizes a compound. A quick example to show how much it stabilizes them is I'm going to show 2 acids here. This is phenol with a pKa of 10. Then cyclohexanol. The pKa is 18. So phenol is 8 times, or 10 to the 8th times more acidic than cyclohexanol is. And what makes it more acidic is if I lose the hydrogen, right, which is what acids do. You lose the hydrogen, you now have a negative formal charge on that oxygen. There's no resonance structure that I can draw in cyclohexanol. But for phenol, I can move those electrons down and bring those up. So then I would get a resonance structure of that. Then I could move these electrons to here and move those electrons up to there. So I can spread this around the entire ring, the electron density, which now allows me to have a more stable compound, because I can draw another resonance structure where those move to there and those move up to there. I can spread it around the entire ring. So that's the last thing to talk about with resonance, is that any compound that has resonance structures is generally going to be more stable than a very similar compound to it that does not have resonance structures that you can draw.